Du så veka. Jag köpte då Sverige där. Det är ju konstigt. Ja, jag ska göra ha. Det enda sättet att få det. Det enda sättet att få det var att köpa. Det är bra. Sen på det är fan ordning av det morse. Subsidiskola. Tjena Bruce! Subsidiskola. Då så kollar jag. Är det din quiz? Ja. Så kollar jag schemat och bara... Den inte? Jo, men vad säger du? Ordning av det. Ja, så såg jag det. Packa upp den och sen ställa i kylen igen. Och mycket i och precis. 5 år på jobb. Ja. Och börjar ju fylla man. Eller jag. För det blir 5 år. Så när vi gjorde det. Sen var det maten och så gjorde vi. Skit. För 20 år. Nej, det var maten. Så skulle vi lägga upp det som man har gjort. Så skulle vi göra det.
Okay, so let's get started. So today we will talk about the final piece of the data link layer, namely the medium access control sublayer, which is a part of that. And this has to do with how to share a common medium, like a radio channel or a cable or whatever, between several transmitters, and different methods for doing that. So that will be the main topic, but we have a little bit of cleanup to do. As you remember, perhaps, I was a little bit doubtful about the correctness of the selective repeat protocol that was in the book. I'm still doubtful about this, so I tried to make the minimal change to the protocol in the book such that it becomes correct. Now, there are many, as you know, there are many different types of selective repeat protocols. So if you read something in the book, if you read another book, if you look this up online, you will get different descriptions of this. But the main problem with the description in the book was that in some cases an acknowledgement was sent with a sequence number of a packet which was not yet received. And this is a problem because the transmitter believes that the acknowledgements it gets are for packets which actually the receiver has received. Okay, so maybe this was a little bit unclear, but anyways, the red text in the following is a correction to the protocol in the book. And the main problem with this was that so this is the receiver logic. If an error-free packet with a certain sequence number arrives, then if the sequence number is outside the receive window, and here was the problem, then the packet was discarded. That's not the problem. But then there was an acknowledgement sent with the sequence number, which was equal to Rn in the book. And that's the problem, because Rn points at the oldest packet not yet received. Okay, and this would then fool the transmitter in believing that this packet has actually been received, and this is the error. So what we want to do then is we would like to send an acknowledgement for one of the gray packets here, one of the blue packets maybe, which is one of the packets that we have already received. So we can, I mean, essentially we can acknowledge any of these, but I think it makes sense to acknowledge the oldest among those packets that we already received. Okay. So that's the modification I did. So I introduced a new variable here, RR, which points at the oldest packet received, but still received out of order. Okay, so these are buffered for future delivery. Now, and another caveat here is also we need to figure out what to do when the receive window is empty, when we have nothing received at the moment, and then we simply don't send an acknowledgement in that case. Okay, so that was the modification basically. So you can read up on this if you like, or you should read up on this because otherwise you will be confused by the book. So this is the modifications done in words, and if you want to look at the state diagram, basically this is the thing that needs to be modified. So when an error-free packet with the sequence number outside the window is arrived, what to do then, right? First of all, we should throw away the packet because it doesn't fit into our buffer, and then we should send an acknowledgement. If we want to send an acknowledgement, we better send an acknowledgement for a packet which has been received. Okay, and this we do by instead of sending RN, we send RR, where RR is defined on the previous page, and then this thing needs to be added also. So if the window is empty, we don't send an acknowledgement at all. Okay, so any questions on this? Maybe this was a little bit quick, but if you look at this and you don't understand the logic, let me know and I'll try to explain it again in some other way. Okay, so let's go on to the topic of today, which is multiple access communications. So what is multiple access? Well, it's basically methods for sharing a medium. Okay, and the medium, what is that? It could be a cable, radio channel, fiber, or whatever. And the sharing of the medium, a common medium, is done between several transmitters. These transmitters are also known as nodes, users, or stations. There are many different names for the same thing. But the main idea is that we have some type of common medium, and then we have a bunch of transmitters. Here, station 1, 2, 3, 4, okay, 5, 6, 7, right? I don't know what 5, no, 5 was out. Maybe we should add this, okay. Station 5 here. I don't know.
We have station 5.
Oh, there we go. Okay, so never mind. Thank you. Anyways, I think you get the idea, right? So we have many transmitters, shared medium. How should we organize this, all these transmissions? Because typically what we would like to avoid is that several transmitters are using the medium at the same time, because then these signals will collide and they could be confused by the receiver. Okay, so that's the goal. So there are different approaches to this media sharing. So of all medium access methods, we can broadly characterize them into two methods. Those who are static, meaning that they are fixed in time for a very long time or for all time, or those who are dynamic, those who change constantly. So if we look at the static ones first, there's essentially just one subclass of this, and this is called channelization. And what we do then is we partition the medium into channels. And there are various ways to do this, but basically we isolate the medium into different channels, maybe different radio channels, or maybe different time slots, or a combination of these. And then we allocate these channels to users on a very long time basis. Okay, so an example of this would be regular broadcast radio. For instance, you know that P1 would be at this particular frequency, and it's been there for, you know, decades maybe, and will continue to be there for many years to come. Every now and then there is a change, right? But very, very seldom. TV broadcast is the same thing. SVT1 has been at the same frequency in Gothenburg for many, many years, right? Okay, so these are one way to share a medium, right? You split it up into radio channel, for instance, frequency channels. You hand out the frequency channels to the transmitters. You keep that fixed for a very, very long time. Okay, another thing one could do is to do this dynamically, so changing in time according to the needs of communication. And this is what we actually would do in this course, because this is it will motivate that more carefully later on, but these are the more interesting ones for us. Then there are two ways to do this dynamically. One is to do coordinated, or sometimes called scheduled access, or one could do it in random access. So let's start with scheduled one. So this is basically, when it says coordinated here, we do careful coordination. So what is careful? Well, it will become a little bit clearer later on what careful means. But essentially what we do here is that before we actually transmit any data, we coordinate the transmissions between the stations, the users or the transmitters that would like to use the medium. And one way to do that is through something called polling. We'll talk more about that later on. But basically, it's somebody organizes this. We have like a master that organizes the transmission among the users. We can also have some type of reservations where it's a distributed coordination of the medium. But basically, these two things here indicate that there is a setup period where we organize how to use the medium, and then we use the medium. So this is used in modern cellular systems, for instance, like in 4G, 5G, LTE, and so forth. Another thing we could do is some type of, it's called random access. And here the coordination is much looser. So basically here, there's less of a coordination phase, I would say. One method would be to simply transmit data when you have it, and then hope for the best, right? And if things are not going well, we transmit the data once more, or third time, or whatever, right? So it's a little bit of a more like loose coordination here, I would say. And examples where this is used is in Wi-Fi, for instance, or on Ethernet, classical Ethernet. So we'll see more about exactly how this is done, right? Okay, so we have static, dynamic. Static, we have channelization. In the dynamic, we have careful coordination or loose coordination. Okay, so medium access control, how does that fit into the protocol layers? Well, we have, you remember that there's the physical layer at the bottom, and above that is the data link layer. And we split that into two sublayers, something called data link control. And this is what we have been talking about earlier. So this is typically where you see an ARQ protocol. If there is an ARQ protocol, doesn't necessarily have to be one. If there is framing, this is where framing is done. You don't necessarily have to do, well, I guess you always have to do some type of framing. Flow control and things like this, right? So this is taken care of by the data link control sublayer. And the medium access control layer takes care of sharing a common medium, a common physical medium. So these things together is the data link layer. Right. Okay. So it's a sublayer. The MAC is a sublayer, and it's responsible for coordination. And when choosing this MAC method, there are many, many MACs, right? So which one should we choose? Well, it depends. So what are the things that are important when we choose the MAC layer? Well, first of all, it's the ability to handle the data traffic that we perceive, right? That we would like to support. And sometimes the data traffic is steady, like it's a common steady stream of bits or whatever. It doesn't change in time. Or it's bursty. I mean, sometimes we have need for a lot of bits to be transmitted, and sometimes not. So steady and bursty, there are different MAC methods which are, definitely good in these two respects. We can have short messages or long messages. Then the medium access control should be adjusted to this for good efficiency. So what we would like to do in the MAC layer is to be good. Okay, so what is meant by good? Well, one thing one is concerned about is delays. Okay, so we would like not to have long delays in the MAC layer. And delays means basically when data is pushed down to the MAC layer, it can be stored here until we get access to the physical layer. So there is some inherent delay in the protocol here. And we would like that to be small, if possible. Sometimes we're concerned about jitter. For instance, in process control, we want the delay through the MAC layer here to be not so varying too much, right? It should be short, preferably, and then the variation around this short thing should be limited also. We also want fairness, meaning that if we have many transmitters, they should share the physical medium in a fair way, right? So everybody should have a chance to communicate. Scalability. That means we should be able to handle many stations. If that is what's required. And so that's one aspect of scalability. Another aspect of scalability is to handle a lot of traffic. Right? So that's also how it scales with when the traffic demand goes up. How does the MAC layer react to this, good or bad? And then we're something called coordination efficiency. We'll talk more about that later on. But basically, we would like to use the physical medium as efficiently as possible. That's the coordination efficiency. And then ability to provide, okay, so QoS, what's that? This is quality of service. So it's a broad term of, you know, the service which are using the MAC layer here have maybe some quality parameters that we should try to respect. Among other things, sometimes we would like the MAC layer to provide priority. So for instance, if you have a common medium and sometimes you have critical services, maybe a fire alarm or something like that going over this medium, and then you have some other service, maybe web browsing, then one would like to prioritize the fire alarm towards web browsing, right? So then the MAC layer could sometimes provide a priority to access. And then, of course, reliability and cost of equipment, that's always a factor. So any questions so far? Okay. So these are important considerations when choosing a MAC layer. And as you might suspect, there is not one size fits all. So there are many different MAC layers who are good in some respects and maybe worse in some other respects. So depending on your needs, you should choose the MAC layer accordingly. For some, static ones are good. For some, dynamic are good. For some, careful coordination is required. For some, it's better to do random coordination or loose coordination. Okay, any questions? Okay, so let's continue then. So one of these performance metrics is delay. So what do we mean by delay here? Well, the frame transfer delay, or MAC-to-MAC delay, let's call it capital T, is the time from frame arrival at the transmitter MAC from its upper layer to frame delivery from the receiver MAC to its upper layer. So basically data is coming down from the higher layers down here to a MAC layer, then go through the physical layer and then over here, and then through the physical layer and through the receiving MAC layer, and then it's delivered here. So the time it takes from going down to coming up, this is the frame transfer delay. Okay. So, and the delays here is due to the MAC and of course the physical layer and the physical layer and the MAC here. If there are retransmissions here due to poor coordination, that is also counted into the transfer delay here. So another thing which is important here is the throughput, and that is the actual transfer rate through the shared medium. So we'll see what that means a little bit more in detail later on. This the throughput is measured in frames per second, how many frames per second that are passing through this physical medium, and then we count the frames that come from all the transmitters which are attached to this one, not only one transmitter, but basically all the things that are going on the physical layer here. That's called the throughput. You know, it could be counted in frames per second or bits per second, and this is always less than the medium capacity. We cannot push more frames through this than the actual data rate, which is supported by the physical layer. But we would like to use as much of that as possible. So in more detail, suppose we have n users, and think of n as being larger than 1, right? Otherwise it would not be much of a problem here. So maybe we have 10 users, 3 users, 100 users, or 1,000 users, who knows, right? But there are many users, more than one at least, that together generate on the average lambda frames per second of, and all of these frames have NF bits. Then the load, normalized load on the physical medium, is the ratio between the number of bits per second that we would like to transmit divided through by the number of bits that the medium supports. So to make this more concrete, suppose we have 3 stations. So the data rate on the medium, say that it's 10 to the 10 times 10 to the 4 bits per second. Okay. So this is the physical medium that we have, and we have 3 stations. And the station number 1 generates on average 3 frames per second. Okay, and all of these frames have a size 10 to the 4 bit. So this is the data which is generated by station number 1, user number 1, and then we have user number 2. Suppose that that generates 2 frames per second to the same frame size, and we have the third one which generates, say, 4 frames per second. Still, every frame is 10 to the 4 bits. Okay. So if we have these 3 stations, together they generate lambda frames per second. So what is that? Well, it's simply lambda 1 plus lambda 2 plus lambda 3. In this case, 3 plus 2 plus 4, that's 9 frames per second. Okay. So that's the total load on the physical medium is 9 frames per second. So the data rate which is offered then is lambda times the number of bits per frame. So that would be 9 times 10 to the 4 bits per second. So this is the traffic which is offered or demanded of the physical medium. Doesn't mean that it's actually supported, but this is what is wished for at least. And then therefore the load in this case is the number of bits that we would like to transmit per second, which is 9 times 10 to the 4. And then we divide through by the number of bits per second that the medium supports, which is R. So in this case is 0.9. So if we have a max scheme, medium access control, which is perfect in the sense that all the frames which are generated are also transferred of the medium, we are using the medium up to 90% of its capacity. Right? We cannot exceed this. We cannot have a data rate, if we offer a data rate which is higher than the medium, that's not going to work, right? Which means that some frames will be queued for transmission and the queuing delay would go to infinity. So basically some frames would never actually be transmitted. So I would say a load on 90% here is quite high. It's quite demanding to find a max scheme to support this, depending on the properties of the medium as we see. So any questions about this? So it's important to remember now, when we talk about lambda here, we talk about the total system, all the stations, the traffic generated by those, which is the sum of the traffic for all the stations. And then the load is the ratio between the data that we would like to transmit divided by the data that we can transmit. And what we can transmit is a function of the physical layer. A max scheme can then support typically a maximum load, and that load is rho max, and it's different for different systems, right? And as long as rho, the offered traffic or the offered load, is less than maximum load, we're okay. Then we will be able to transmit all frames. But if we violate this, then the system will break down. So in practice, it's important that the offered load has some margin up to the maximum load. Otherwise, things will be overly congested on the physical medium and bad things will happen. And of course, rho max would always be a number less than 1 due to the coordination loss that we have over the medium. There will always be some loss here. And then the transfer delay, the time it takes for one frame to come in and the same frame to come out, this one typically increases as the load increases. And why is that? Well, it's because when the frame comes down like this and the medium is heavily used, there will be a lot of waiting time in the Mac before it's actually transmitted. And also counting the problems that if it goes out on the medium and gets damaged due to collisions, then there's a retransmission protocol, and that would also introduce more delays. Okay, so then let's look at what causes this coordination inefficiencies. And I mean, you can think of it like this. The Mac problem is like this. Suppose we are all stations in this room. We put on our blindfolds, and then we would like to communicate with each other. And to coordinate that communication is not trivial, because there will be some delays between people talking, right? So if I start to talk, you are not aware of that I started to talk until the sound waves have reached you, right? So, for instance, if you ever talked on a phone with a large delay, you know what the problem is, right? It's easy to start to talk at the same time, in the sense that you start to talk, but you're not aware of that the other person has started to talk until the signal has reached the other end, right? And the same thing is in here. It's the propagation delays over the medium that causes problems in coordination. Okay. So, suppose we have a medium here, and think of this as a cable, right, for simplicity. It has a certain length from end to end, which is d meters. And then we have a number of stations. Let's call them, m stations, a bunch of stations here. And then the propagation delay is the delay from the left-hand side to the right-hand side of this. Okay. And then the propagation delay is the time it takes for a signal that comes from one end to be received at the other end. So then the propagation time, t-prop, is the distance divided by the speed of propagation. So even if the speed of propagation, it could be quite large. I mean, it could be a sizable fraction of the speed of light. These delays are actually problematic. Right? And we can never, ever, of course, send a signal which has a higher speed than the speed of light. Even people have tried. I can say that no one has succeeded in this yet. Right? So it seems to be a fundamental barrier. So for instance, if this is a satellite channel, this delay could be quite substantial, right? Now, on the medium, we have r bits per second. It turns out that the critical parameter here is this parameter a, which is let's go to the right-hand side. It's the ratio between t-prop and tf, where tf is the time duration of a frame. Okay, and one can write that also as r, the bit rate on the medium, times the propagation delay divided by nf. Okay, and this simply follows from here that I mean, if we just plug that in here, we get that result. Okay, so this is called the delay bandwidth product. Okay, bandwidth, because in data communication, r bits per second is sometimes called bandwidth, and t-prop is a delay, and then it's normalized with the frame size. So sometimes it's called a normalized delay bandwidth product. But how can we interpret this delay bandwidth product? Well, say that a simple example of this, suppose we have a propagation delay of 1 millisecond, right? And that could easily happen if we have a long enough fiber or whatever, or a radio channel. The distance between transmitter and receiver is 1 millisecond, say. And then we have a data rate, say, of 100 megabit per second, which is not unreasonable. And then say that we have a frame size of 10 to the 4 bits, 10,000 bits. Also a reasonable frame size. I mean, a normal IP packet is about 1500 bytes, which is 12,000 bits. So then, from this, we conclude that the frame duration is what? It's NF divided by R, right? The number of bits divided by the number of bits per second the medium has, it can support, and this is then 10 to the minus 5 seconds. So then, what can we say about A? Well, A is T prop divided by TF, which is 100 in this case. One interpretation of this is to think of this in time. So if we have T prop here, how many frames can we transmit during T prop seconds? That's the delay bandwidth problem. So we have, in this case, a fairly short frame duration compared to the propagation delay. So we can put here A frames, right? Another way to think about this is to think about the medium as a bit type. Okay. And the bit type has a length which is equal to the propagation time. And it has an area here which is R, the data rate that we can transmit with. So this is in bit per second, and this is in second. Then, if I push in on the left-hand side a packet, a frame, it will go through the medium, and it would then occupy TF seconds like this. So at any point in time, if I push in frames from the left-hand side, there are 8 of those frames that could be in progress towards the receiver. So the medium itself stores up to 8 frames. Okay, in this case, 100 frames. In the medium itself. So any questions on the delay bandwidth product? And the reason, okay, and now we can start to think about why is this a problem when we have a large A? Well, if we want to coordinate transmission from this end to this end, it takes 100 frame durations before somebody on this end knows that a frame has been transmitted from the other end. So here we have these large delays between 2 ends of the medium, and that causes problems in coordination. Okay. And the thing is that coordination, how is that done? Well, it's done over the medium. We use the medium in order to coordinate the medium. So it's like it's a circular argument or tail biting or whatever. It's that's the problem here. We use the medium to coordinate the medium. And if the medium has a lot of delays in it, this is problematic. This is difficult. So, I mean, this is a PowerPoint slide, so this doesn't show a real max scheme, but essentially the transfer delay is a random variable because it depends on data traffic, and data traffic is typically random. So the frame transmission time, duration TF, is NF divided by R. The transfer delay typically increases dramatically as the load goes to rho max. So when we start to use the medium more heavily, the delays goes up. It's quite natural, right? And so if we have a scheme, a max scheme, it has a maximum load. And if we have a load which is far away from the maximum load, then the transfer delay normalized with the frame duration is basically 1. Okay, so there is no delay in coordination. The max scheme doesn't introduce any delays because it doesn't have to, because the load is very low, right? We have a super nice physical layer and we don't use it to nearly even close to its capacity, right? And then delays are pretty much negligible. They're only due to the transmission duration. But then as we start to increase our load, more and more data is pushed onto the medium, meaning that we have more and more users of the medium. Because remember that the load has to do with the aggregated traffic on the medium, not necessarily the traffic from one station. But as we go here, approaches rho max, then the delays becomes more and more. And this has to do with that it takes time to coordinate the medium. And there will be collisions perhaps and ARQ problems. Okay, so then it goes something like this. Now, rho max itself, it turns out that this actually depends on A. So as A increases, rho max decreases. Okay, so what is the interpretation of this? Well, it basically means that when A, the normalized delay bandwidth product, increases, it's more difficult to coordinate the medium, and our ability to do that efficiently decreases also. So rho max for most max schemes decreases when it's more difficult to coordinate. But it also makes sense, right? Okay. Yeah. So this is say like the overview type of consideration. So let's see how this works in practice to reinforce this, that this is actually what we said earlier is actually true. And the simplest possible max scheme we can think of is a scheme where we have 2 transmitters and a common medium, right? We only have 2 transmitters to coordinate. So we look at the simple 2-station example. We assume here, for the sake of argument, that we know the propagation times. What is the propagation time? Well, it's the time it takes from a signal from station number 1 to reach station number 2. And if they are on distance d, then t prop is d divided by v prop, where v prop is the propagation speed here. Okay. Now, I will state what the protocol does and then motivate why it does this. Well, first of all, a station that would like to transmit, say station number 1 would like to transmit, before transmitting actually the frame, it listens to the medium to see if there is any ongoing transmissions. If the medium doesn't have any ongoing transmissions, it's free from the perspective of station number 1, then it starts to transmit a special signal, a reservation signal, this reservation signal, and it does that for 2 t-prop seconds. And why this is the case, we will see shortly. But it starts to transmit a signal, and this one goes over the channel, and then is eventually picked up by station number 2. It listens to the medium during the transmission of this reservation signal, and if it detects a collision with some other reservation signal, then we know that this one started to transmit a reservation signal, this one too, at roughly the same time. Okay, and what happens then is that we have a collision. Now, if there is no collision, then that's fine. Then we can just start to transmit the frame. If there is a collision, then we give priority to the station that started to transmit the signal first. Okay, and this is actually possible to do by processing, local processing in station 1 and station 2. We'll see this shortly. And then after transmitting the frame, the transmitting station is silent for a certain time. And this is needed so that the other channel can, the other station can also use the channel. So this is out of fairness issues. Okay, so let's see how this works. Okay, so this is A, station number, yeah, maybe. So this is A here, right? So this is A and this is B. Change the notation a little bit stupidly, but anyway, so we have the first station and the second station, and then we have time axis like this on these two things. Okay, so now suppose we start and nothing is happening on the medium, and then station A at this point in time has a frame that it would like to transmit. Before transmitting the frame, which is the green part in this diagram, station 1 starts to transmit a reservation signal. So it starts to transmit the reservation signal here. It goes over the medium, and then after t-prop seconds, it arrives at station B. Okay. Now, station B, on the other hand, is also trying to transmit, because at this time, station B has a frame ready for transmission. It listens to the medium is idle, right? There is nothing going on the channel here from the perspective of station B. Station B has no idea that station A has already transmitted something, because it cannot, right? It will learn about that here, not here. So station B also starts to transmit, and then we see at this particular point in time, collision starts to happen on the medium. Okay, these signals are then propagating from each side, and they meet somewhere, and then they keep on going in the other direction. So station B's reservation signal keeps on propagating up here and reaches A at this point in time. So at the purple point in time here, okay, so let's backtrack a little bit. So station A, who started to transmit the reservation signal earliest, here at this point in time, the red point in time, station B knows that station A has transmitted because it can see the signal here. What does station B do then? Well, it stops to transmit its reservation signal. So it stops here. So the last piece of the reservation signal for station B reaches A at this point in time. Okay, and so at this point in time, station B knows station A want to transmit, right? At this point in time, station A knows that station B wants to transmit. So what to do? Both of them want to transmit. So which one should persist and which one should cease? Well, the logic is the following, that station B here knows that it started to transmit its frame here, and it noticed that the reservation signal came from station A at this point in time. The difference between these two times, if that's less than a propagation time, station B knows here that station A was first. Conversely, here we see that station A knows that the difference between when it started until it heard the reservation signal here, this is larger than a propagation time. So here station A knows, okay, I have priority. Right. But then station A still has to wait until the reservation signal has stopped coming from station A before it can start to transmit its frame. And it starts to transmit its frame here. It goes over the channel, and then it's received at station B at this point in time. So at this point in time, we are complete. The transmission from A to B is completed at this point in time. Okay. Now, suppose station A has another frame to transmit, it still needs to wait for propagation time before it can start to compete for the channel again. Otherwise, station A might seize the channel and keep on using it forever, never letting station B come in. Okay. So any questions on the logic here? I would say this is a quite important example. If you understand this, you understand a lot of the medium access control problems, right? And it has to do that an action at station A is not notable at station B until a propagation time, in worst case. That's the problem, right? So the action on station B is not noticeable at station A until a propagation time has passed. Okay, so then what is the row max for this medium access? Well, we see coordination here is perfect in the sense that this frame will always be transmitted without collisions. So assuming that this frame is always delivered correctly, ignoring noise and whatever, then we can deliver NF bits, right, error-free, during the time from here to here, which is TF plus 3 T prop. This is the time it takes to deliver the green frame here. So the data, useful data on the channel is NF bits are delivered in the time TF plus 3 T prop. Okay. And rho max, the maximum we can do is that if we repeat this over and over and over again, then we get, we use the medium with RU max always and divide that by R, and we see it's 1 plus 1 plus 3A, where again, this is the loss due to the coordination, okay? And we see that the loss depends on A, and A is the T prop divided by TF. Okay, meaning if we have a large propagation time compared to the frame duration, then our rho max will decrease, as we said earlier, right? If you go back a few slides, you see that when A increases, rho max decreases, which means that we cannot, the efficiency how we use the medium is decreasing for this protocol. And that's actually true for most protocols. Questions? No? Okay, so let's take it then 15 minutes.
Mm.